All right, good morning, students. We are starting the lecture. Session has been recorded. I'm just going to throw a quick poll out here. You see it pop up. Who has completed the homework tutorial? Any questions with this one? Obviously, I'm asking this for a particular reason. Who's completed the homework tutorial? Should I show on inertia systems and on inertia systems? Accelerating inertia systems. Poll should pop up. Just respond quickly. Yes, I'm proud. Yes. Just getting yeses, cracking up here. Fantastic. Any no's? So I'm just trying to discern whether I should work through it or not. There's one no. Well, make sure you work through it. So we're doing 6 more responses. All right, so to show you the responses, well, you can roughly see that most students have completed it, and I'm assuming they've got the right answers. However, I'd like to ask you guys, are there any questions within the tutorials? There is something which I wanted to bring up. What kind of results were you getting? Let's talk about number 2. Guys, you can engage here. So obviously I gave you a setup. It's a 2-body setup. One mass, one bigger mass and a smaller mass. System accelerates to the left, and then at number 2, I actually asked if what happens if angle C increases to 60, right? And the idea was for you to predict the outcome before conducting your analysis. And what answers did you get in number 2? So I'm just going to highlight something, and I won't actually particularly solve it. If I need to solve it, I'll do that. I think everyone has managed. But at number 2, right? What was the acceleration and what was the tension? Of course, why is this important? Can someone just give me that? Ms. Pandey, what do you get for your acceleration and tension at number 2? Yes, thank you, Mr. Duplessis. You can say that. What is the magnitude of your acceleration and your tension? What did you get? Yep, that looks legit to me. 0.725 maybe, could call it 25. Yeah, 725, that's fantastic. Meters squared per second. Negative, and then what's your tension? I just want to talk about that quickly. Tension should have been around 46 newtons, right? You guys get that? 46.24. Okay. So can I ask you a question? And you guys can unmute your mic and engage if you'd like. What does a negative acceleration mean? Right. So this is the kind of higher order stuff I might engage you. I might engage with. And this is why I deliberately created this tutorial to see. What does a negative acceleration mean? Mr. Asa, you can go for it.
I think it means that the direction that you assumed is different from what you got. It's in the other direction, opposite direction.
Fantastic. And what direction is that in that case?
Uh,
Left or right? It's going right.
It's gonna be right, yes.
Yes, exactly. Thank you, Mr. Asa. So, guys, that's a very important question. In your first test, yes, the magnitude is still be correct here. Yes, the tension is still correct here. That's more about the direction. Um, just to unpack that further, if you actually think about that, is this a question? Mr. Asa, are you raising your hand or are you lowering your hand? Okay, he's just lowering his hand. Okay, you can ignore that. So what it means is that the system, as we increase this angle to 60, and I mean 60 is quite steep, right? So I'm just gonna try to get that all right. And then other one is like around. I mean, you want to really get it spot on here, and you have to just move shift it around. That's around 30, and I mean it's quite steep, around 60 degrees, right? Just bear with me here. So obviously, if this goes higher up, the incline I mean, the weight components will shift a bit, right? So the tension is the same. However, what you're going to find that the system is going to be accelerating this way. So that's what the negative means. Obviously, it means it will accelerate in the opposite direction of what you've assumed. And it kind of makes sense. So you have picked that up at a few cases. For instance, a negative acceleration, I think, would have been at number 2. So you get a negative acceleration here. So obviously, we're just discussing this concept of negative acceleration if it does arise. I think also you have gotten it over here. I think where all the black I've highlighted is also negative acceleration. And I think maybe here. I'm not sure. But for sure, these two should have gotten a negative acceleration. So why am I making you aware? So when you see a negative acceleration within your tests or exams, please be aware of what's happening, right? It might be undesirable to have a negative acceleration depending on the application of this thing. But obviously, this is just a exercise, and I wanted to make you guys aware that you can get the tensions are always typically positive. That's never going to be a problem. Obviously, your tension is affected by your acceleration because of F equals ma. And would the magnitude still be correct, or the tension magnitude? Yeah, so the tension magnitude is also correct. Yeah, okay, cool. So Tajrik, I hope I answered the question. Is there any questions with this particular tutorial? I mean, I guess everyone has done it. Does everyone understand the concept of what this negative acceleration means? It goes in the other direction. So we should say moves in opposite direction, right? Let's get it right. Moves in the opposite direction. Or rather, moves in the opposite of the assumed direction. Right? So if you assume left, it goes right. If you assume right, it goes left. Answers confirmed in the prescribed textbooks. Yes, Mr. Shongwe? I've recognized you. You can go for it. Okay, Mr. Strong is not saying anything. Yes, acceleration is 0.42. Answer is confirmed in the prescribed textbook. Yes, Tashrik. I don't know what you're referring to. You're referring to number 2, not the actual first part of the question. So there's a lot of sub questions I've put out here from 1 to 6. So I'm referring to those over there. And number 2, you've gotten a negative acceleration of 0.725. So that's the what you're seeing there is the first part That 0.42 is over there. I hope that's clear to you. See the strongest hands is raised. Okay. Just one more. Yes, Mr. Duplessis. You can go for it.
Yeah, good morning.
Good
With the
morning.
negative acceleration, do we need to change it over and do the whole calculation as if it, or with the change the direction?
No, but once you get the answer, it's fine. I'm just giving an explanation of like, okay, so we have a negative acceleration. What does it actually mean? So you mustn't get all bummed out. So what does it mean the system accelerates the other way? That's all. You shouldn't actually just change your thing. And the idea was for you in this particular exercise to look at the thing and you say, okay, if I increase that angle at C to 60 degrees, what will probably happen to the system? And obviously you make that quite steep. What you tend to find is the 5 kilogram mass would actually pull the 15 kilogram mass. Similarly, if you actually have a mass at C, increase the size of the mass and you actually find that it can actually pull the other mass. So that's all, Mr. Duplessis. Is 2.3 also negative? I'm not sure. Don't think so. Yeah, it should be positive. It should be positive something. Yeah. It's a positive acceleration. So please have a look at that. Is there any other questions before we move on, students? Before we move on to the next chapter. I think this is all not self-explanatory, but I thought I'll make you aware of this. So I'm glad you guys have. No, so Vian, you don't have to change your frictions around. And no, it's the analysis you're doing, Vian, is just at a particular instant, right? So you're not required to redo it over again. Just you're doing it at that particular moment. We're assuming how it's actually moving. So it's just, yeah, it's a good point to make, but don't worry, I'm not expecting you to go it's not going to be super complicated. It's just that, okay, what it means is that the system is actually moving the other way. That's all what it means in that case. Nothing complicated. Okay, guys, I think I'll take one more question and then we can move on to the new chapter. Morning, Mr. Silver. So, guys, I highly recommend being behind a desk. I should have probably mentioned that you can't be sitting in the bed watching these lectures, getting your notepad out. We will be solving problems as per on-campus lectures. So, yeah. Okay, no questions? Cool. Let's begin. Right. Okay, guys, I'll just give you 2 minutes to just get yourself your bearings in. My slide should be up and we'll officially start the new chapter 2. So this chapter will spawn across 2 weeks. We have a part 1 and a part 2 next week. Probably the second part will be on campus, but we'll decide on how it's going to work out. Yeah, just so I can engage with you again. All right. If you guys are all good, we can actually move on now. So just give it a minute. And we have enough time for today, so we have some breaks in between, so we won't be sitting behind our laptops all the time. Okay, without further ado, let's begin. So the chapter is called Relative Velocity. Let's see what this is about. So before I normally, start the chapter, I always try to have some questions. So let's look at the first diagram, right? So Mr. Duplessis likes to fly aeroplanes. And as you can see there, we have 3 different, what's the word I'm looking for? 3 different scenarios from the left to the right. Let's look at the one on the far right. What do you think is happening to the plane? Well, what are you noticing what's happening with the plane over there, with Mr. Duplessis as he's flying? Can anyone tell me? Mr. Asa, do you have any ideas? PJ? Ashrik? What's actually happening over there?
Yes, sir, the plane isn't flying in a straight line.
Fantastic. Why do you think that is?
Due to wind.
Yes, there we go. Who was that now? Yes, Ms. Panje, go for it.
Yes.
Just hold on, Mr. Casimiro. First Ms. Panje and then you.
I was literally going to say the same thing.
Okay, great,
Yeah.
fantastic. Mr. Casimiro.
Yes, as I was saying, is it's kind of being shifted due to wind velocity.
Wind velocity. Okay, so we're talking. This is what it's about. So if you also look at the guy with him, Ms. Panje running in the rain, right? And as she's initially standing there, I mean that looks like a guy, but okay, just for give the example there. And as she's running, it would seem that the velocity of the actual the rain would change, right? So as you're standing still, and then as you begin to move, you'd find that the velocity would change. It looks like it's coming at an angle instead of coming, even though it's still falling down. It's still falling down, but as you run, it looks like it's coming at an angle. What we're touching on is a lot of this kind of stuff, right? So topics we'll be discussing is with around these things. If you remember, I did mention something about a net force, and if you remember that three guys pushing a box in the lecture, and you could see that even though the one guy was going to the right, to the left, other one's going to the right, and other one's going up, you saw a net force. So it is within the same domain of thinking. Okay, so let's move on. So relative velocity. So, and you're going to start talking about, anyway, so they're saying that what happens is, so what you can imagine is one car A doing 60 kilometers and another car at B doing 80 kilometers, right? What happens is they're approaching each other. So they're saying, so what the text is saying is, so when you're in a car doing 60 kilometers and another car is coming down to you, towards you, having at 80 kilometers per hour, the two vehicles are approaching at 140 kilometers. Do you guys agree with that? What do you guys think of that? What do you guys think of that? Yes, Ms. Panje?
So, can you please repeat your question?
Yes. So, by basically, we're just looking at that particular image over there. So you've got two cars over there, right? And they're approaching each other at 60 kilometers per hour and another one in 80, right? And what I'm proposing here, what I'm advocating, I'm saying the two vehicles are approaching each other at 140. So that's what I'm saying. Even though they obviously they're driving at speeds of 60 and 80. So I'm asking you, do you agree with that statement? That's all. Ms. Panje, you're not saying anything now? Are you thinking about it? Yes, I agree. Okay, Ms. Panje, we'll talk about it. So what they're saying there is that neither car is obviously moving at a speed of 140 kilometers per hour relative to the road. It's not true. However, what is actually, yes, you get the concept. You'll see it's fine. They say, however, to the occupants, both of the cars appear to be approaching at 140 kilometers per hour. You say the other car's speed relative to us is 140. So that's very important, right? This is the concept of relative velocity, and obviously we're gonna get there. So I'm just making you aware of what it is. You have to imagine yourself driving and another car driving, and it looks a lot faster than what it actually is. So it's an interesting concept, but you get it. So this is what relative velocity is essentially about. But before we get into relative velocity, we need to touch on something called resultant velocity. All right. So just to make you guys aware why relative velocity is particularly important. The main thing, what this particular chapter is building just the fundamentals for the next level of mechanics of machines. and it's basically used to find the magnitude and direction of many things. For instance, one machine part relative to another. So we have a typical 4-bar rocker mechanism over there to the right. We can actually find, using relative velocity analysis, the velocity of each section at a particular instant. Yeah, so that we actually cover in Mechanics of Machines 3. We can even find the velocity of a machine tooltip relative to the material being processed. Another example would be the velocity of a fluid relative to a turbine blade or propeller that is moving. Obviously, we need to know the velocities. Obviously, mass times velocity gives you the amount of force. Force will eventually relate to some kind of stress, and stress will basically tell us what's the limits of what's in our material. So I'm just making you aware what this chapter particularly is. It seems very isolated compared to the rest of the syllabus. However, it's just kind of a fundament for the next level. When you do in mechanisms, essentially, we do a relative velocity. So I'm just making you aware of that. Okay, so before we begin, like I said before, we need to delve into what relative velocity is. I'm not sure what to call the chapter relative velocity. We need to understand the concept of a resultant velocity. So obviously we touched on this a bit, especially with our plane over there and our small example with the spine here running through the rain, is that what the resultant velocity actually is. So I'll just give you a quick example. So I'll just take you to the figure on the right there. So Ms. Pine again, once again, she's crossing the river. She's going straight across the river, which is A and B wide. We don't know the width yet. And what's happening there? There's a tide, and the tide is going towards the right. So what do you think is going to happen? Do you think Ms. Pine is going to go straight across, or is she going to be going? Is she going to go perfectly straight across, or what's going to happen? What's probably going to happen is that she's going to be moving the resultant velocities of the tide itself in the river and also the boat, right? That's what's important. So she'll be actually drifting at an angle, right? So what they're saying here, just read the text. You said, for example, suppose you're rowing in a boat trying to cross a river, starting at point A and aiming at point B, obviously going straight across. And saying you'll be rowing at 3 kilometers an hour at right angles, but the current will be moving at 5 kilometers per hour. Obviously, this should be meters per second. So the idea is that you've got a right angle component over there. And they're saying you'll not land exactly opposite at the bank B, but you will land at point C, downstream from there. They're saying this is because of actual velocity, namely velocity relative to the Earth, and we should talk about is the vector sum. Very important, guys, not the algebraic sum or arithmetic sum. It's the vector sum of the two velocities mentioned as you travel. So this is exactly analogous to these examples over here, right? Cool. I hope everyone understands this concept. Is any questions with this? Because this is what the concept is essentially about. We start unpacking now. No questions? Just you can always give me a thumbs up in the chat there if you're happy. Just understand exactly what the resultant velocity is. Okay, anyone? Guess everyone's happy. Thank you. Yeah. So again, another example. So it doesn't always have to happen at right angles. For instance, here we have a tailwind. So tailwind basically means at the back of the plane we've got a wind pushing. So what they're saying here, and Ms. Pine help you in the grasp this, they say to illustrate this principle of resultant velocity, right? So they say tailwind is merely a wind that approaches from behind the plane, and then the resulting vector, right? In this case would be, so we've got a plane traveling 100 kilometers per hour, but you've got a wind velocity of 25. And then the question is, then what is the velocity of the plane relative to the observer on the ground? So remember, again, now we bring the relative part in, right? So relative to the observer. So when you're standing on the ground looking at the plane, the actual velocity what you're seeing is going to be 125. Do you guys agree with that? Right? Boom. Relative to the ground. Yes, there we go. Relative to the ground. Yeah. Remember, the plane's only traveling at 100. The wind's only at 25. But relative to the ground, you are seeing 125. Right? So that's the resultant. And we're going to talk about this concept of relative, but I hope you understand what that means, Ms. Pange, or not. Okay, so here they're saying the resultant velocity is basically, it's the result of the wind velocity contributing to the velocity of the plane's motor, right? So instead, the plane is only driving 100, the wind is at 25, tailwind behind, but when you're looking at from the ground up, you're seeing a total of 125 kilometers per hour. That's what you actually see, right? That is one concept of resultant velocity and of course relative. So if I could ask you, what is your velocity relative to the wind? Who can tell me? Anyone? Your velocity relative to the wind? 100 exactly. It's 100 kilometers per hour relative to the wind. From the ground, looks like you're going faster, right? So just bring out the concept of relative, sliding it in here, what the idea of resultant. We're going to be focused on resultant and then you'll get it all right as time goes on. Nice. Okay. It is a bit of a weird one, but yeah, you get used to it eventually. Okay, so in this case, and I like also more students to engage. In this case, we have a headwind coming on, and a headwind is basically a wind approaching the plane from the front of the plane, right? Again, relative to the wind, our plane's velocity is still 100. And obviously, if you're from a observer looking at the ground, the wind is actually slowing the plane's velocity, right? So it would be in this case 100 minus 25 is 75. And of course, the resultant velocity in this case is 75, and relative to the ground, that is what you see. Okay, does everyone get this concept so far? Right, I'm trying to throw in the relative and resultant things. The resultant in this case on a headwind at 75 kilometers per hour, even though you think you're going 100, 120, you're not actually going 120. That's actually sometimes when you're driving as well, the wind's actually slowing you down. As a more on land example, I'm not sure. So relative is the air through velocity which you should be traveling. Yes, of the plane basically, yeah. So it's depending where you look here. So relative to the air, relative. That's why what's important is you seeing this over here, the boat. So if you look at that image of the boat at the bottom, you in the boat traveling at 3 meters per second, for instance, but you're not actually traveling 3 meters per second. Yes, in the boat you are, but relative to someone standing on the ground, they can actually see you shifting at a particular angle. So relative to the ground, you're actually moving at a different velocity as compared to what you are actually experiencing. So that's what it's about. So that's why the concept of resultant needs to come in along with relative velocity. Cool. I hope that's explained. Similarly, we've obviously saw a plane, and of course now we have a side wind, and it's exactly the same thing again. We've got a plane going forward at 100, but now we have a perpendicular wind velocity vector traveling at 25 kilometers per hour. And as that is happening, it's resulting in the plane shifting. So we have to basically take the resultant of that, which is the blue R over there. And instead of traveling 100 kilometers, we actually start traveling a bit faster at 103.1 kilometers per hour. So can you see that's quite interesting? And we're actually traveling at an angle of 14 degrees. So obviously, we just took the tan over there, the tan of 25 over 100. So again, relative to the wind, we're traveling 100, but from the observer standing on the ground, we can actually see the plane moving. At an angle, or you can't actually really see it. I mean, depending where you stand, but if you had to look from the top of the plane in space or just above the atmosphere, you'd see the plane actually shifting 14 degrees away from that axis it's supposed to be driving. Okay. Is this concept all clear, students? Is there any other questions with this concept? So the concept we bring out is the concept of resultant, which you're kind of aware of, and the concept of relative velocity. That's the two things I'm bringing out here. Any questions, students? It's fairly simple to kind of understand. So this means we have to travel 103 to. I like that. Let me just read it. So that means we have to travel 103 kilometers to cover the same vertical distance without the wind. Yeah, we have to travel 103, and we're going to be doing examples just like this. So what I like, so what Tajriq saying, if for us to keep on going straight, right, perfectly straight, assuming there's no wind, we have to travel at 103 kilometers at an angle of 14 degrees, Tajriq. So the wind will compensate, the wind will keep us straight. So we have to actually travel at the resultant, and then the wind is going to push us. The wind is going to push us straight. Does it make sense? Nice question. Nice question. So we're gonna adjust our, I don't know, our steering on the plane to run 14 degrees, right? Obviously on our compass over there, and increase the speed a bit, so we can actually drive 100 kilometers. That's a very nice question. Did everyone get that? I'll unpack it if I need to unpack it. It's a very important concept. Yes, fantastic. It's important because sometimes some of these questions is going to ask at which angle must you travel, basically to ensure that you go across. And if you master these small fundamentals, you're basically going to get it. So I'll repeat that again. So what Tajriq is asking is for us to compensate for the wind, essentially. What we have to do is travel now at 103.1 kilometers per hour at an angle of 14 degrees. And what's it going to do is that the wind is going to actually push us back, kind of push us back straight, so that we can actually keep at 100 kilometers per hour, which is required, or we actually want to go straight. That's exactly the same with this example over here, with that motion of the riverboat at the bottom. What it essentially means is that we got to travel at an angle so that the tide can push us again straight in. So that's the two concepts you're looking at, right? The resultant part, and also the resultant part, and also the idea of what the relative velocity is. Yeah, and just basically giving you the summarized examples of each particular one of what has happened. So this is the concept we're going to take, and we're going to be using it right through for the rest of the chapter, essentially, right? Okay, so let's just describe a few things. Yes, Ms. Pani.
Okay, so this is, if you say this is the resultant is what we have to travel at to get to keep to the 100 kilometers, then
Yeah.
what for a side wind, what would be the relative velocity? What is the actual relative to the ground, the velocity that someone on the ground sees?
Yeah, so on the ground, what someone's going to see is always the resultant velocity, Ms. Pani. Are you with me?
Okay.
The resultant velocity is, yeah, that's the point of that. So on the ground, people see the resultant velocity. Again, reaching back to this example, in a boat, you're not really seeing yourself drifting, right? But some on the ground or on the top, maybe in the sky, a bird sees your boat shifting at an angle. Or I can just use that again as an example over there. So the resultant is typically the one at the ground, and if you're saying relative to the wind or relative to the boat, you're actually still traveling at 3 meters. Relative to the ocean, you're still traveling at 3 meters per second.
Okay.
So important concept, just understanding resultant, yeah, and relative. Unpack that nicely. The calculations are not too bad. It gets a bit can get a bit crazy. I hope you got that. Cool. So what's important before we move on to doing all the analysis, we must just talk about a few things that's important. And obviously we're going to be describing the directions of velocity vectors, because we need a place to obviously organize their movement. And obviously we've always adopted X and Y Cartesian plane. I mentioned that typically for linear type motions. And obviously we can convert that Cartesian plane into obviously a north, south, east, west kind of setup here, right? So just a few notations I want to talk about. So let's look at the first image on the left. And they're saying, for example, in the first illustration, if you start at east and you're moving towards north, you describe it as east 32 degrees of north, right? Very important, because sometimes your vectors will look like that. The question will say east of north or north of east, right? So then for the same thing, we can look at the same one. Obviously 90 minus 32 will give you 58 degrees, and we can also describe exactly the same vector over there as the body is moving 58 degrees north to east. So the E will tell you, relative to where the vector is actually moving. So they're saying that these two expressions mean exactly the same thing. The point is to basically to describe the direction fully, and it's a reference to the principal axis. So I hope we all got that over there. So if you look at the one on the other side, we're going to say west 75 degrees from west to south. That's what that means. Alternatively, we could say south to west of 15 degrees or south. I don't know how you guys would like to say it, but I hope you guys understand referencing the vectors. Are you guys comfortable with this? Does it make sense to you? So east of north tells you the principal east. It tells the first direction and tells you where it's going to, basically. East of north at 32 degrees. Is everyone comfortable with this? You'll be seeing it coming up a lot. Yeah. Okay, great. Thank you. South of west, and yeah, you'd see it described like that. Yeah. Okay, another way of describing direction of a vector, obviously the speed is fairly easy. I'm not going to talk about any measuring equipment, but we know what it is. Obviously a compass bearing, and what's important here, we can also go directly to the compass, and we know that 0 degrees would be north of east is 45, east is 90 degrees, south of east is 135, south is 180, southwest is 225, west is 270 degrees, and north of west is 315 degrees, right? Basically goes clockwise. And what they're basically talking about there is like using another illustration. If you look at ship A, we say it has a bearing of 120 degrees. So that's what we actually call it, a compass bearing, right? And then if you look at ship B, what are they saying there? They're saying ship B is where ship B? Oh, they're saying ship B is proceeding on a bearing of 65 degrees, which is correct. Obviously it's 90 minus 25, but they also say the rock as seen from ship B is at 290. So that's more something about the relative bearing. So we also have something called relative bearings, where sometimes I don't optimally go for it in my questions, but the idea is that relative bearings, again, it's like a similar concept to relative velocity. So if you look at the overall bearing, you would say that it's the boat is having a compass bearing of 65 degrees, right? But relative to the boat itself, there you can see a rock at 20 degrees. Oh, sorry, the rock's at 65, the boat's actually at 45, and relative to the boat, we can see the rock at 20 degrees. Obviously, relative bearing is important, depending, especially on the navigation side, is a whole big thing of the whole bearing, and I know the gyroscope and all of that, and then getting another bearing and then working out all the bearings and stuff. But just make you guys aware of, you'd see it come up in the, and sometimes when you describe a resultant velocity, you have to say in which direction or which quadrant, or specified in a bearing, specified as this kind of thing, south or west. Cool. Another thing which is a touch on, it's not something particularly important, but it does come up. I don't want to shock you. The only reason why it's here, it just brings some maritime type applications. Guys, we nearly did solve the problem, so don't worry. Just what a knot is, and a knot is a measurement of speed, and it's equivalent to 1,852 kilometers per hour. And from what I understand, Mr. Naidu told me back in the day they used to have a long rope with a lot of knots on, and you throw it in the water, and as a ship moved, it actually count how many knots on the rope was like immersed or not immersed. I'm not particularly sure that works, but that's what the idea is. It's just the way that is where it traditionally came from. However, the idea is that also 1 knot is 1 nautical mile per hour. And the whole idea of the whole nautical mile thing is that, you know, the earth is not a square, or it's not flat, and a nautical mile essentially is it's 1 length of an arc at the earth's surface, right? So nothing too big. And then obviously, and a nautical mile is 1,822 meters. Obviously, 1 nautical mile is 1 knot. But you might see these what's this? These alternative sea-based measurements on the some of the questions. But particularly I normally keep it kilometers per hour. But there are 1 or 2 questions in the tutorial. So yeah, just to make you aware of that. All right, so we're nearly there. Again, now probably should have taken this and thrown it to in the top of the slide, I'm feeling. And what it says here is that there's no such thing as an absolute rest or movement, but only relative motion. Everything moves relative to something. And the same velocities relative to the Earth are referred to absolute velocities. That's a equal absolute velocity. So whatever from the observer on the ground, that is what we deem as absolute. That is point zero. And the term relative applies to motion of one point relative to another. And obviously, I threw that conversation in between the illustrations I made there. And obviously, they're saying the velocity of a body is always measured with respect to some coordinate system or frame of reference. And they're saying the absolute velocity of a body can only be measured within one frame of reference as an absolute rest. So obviously, they're saying, example, if you measure the velocity of a moving body on the Earth, the velocity of with respect to the. So basically, we are using the Earth as our means of our ground reference, but that is not particularly true because the Earth is also rotating. So the Earth is rotating relative to other planets, or in fact, the Earth, all these planets are rotating around the Sun. But we are just saying that the Earth is our reference point, and the absolute velocity or the resultant velocity typically is that. So just to make you aware of relative to this, relative to that. Sometimes you make one thing stand still and see how the other body will conduct itself. All right, just nearly summarizing the concepts. Number one, the resultant velocity is the vectorial sum of the velocities. Keyword vectorial sum, and we're not algebraically summing anything. The relative velocity is the vectorial difference. So that is something interesting we'll talk about, and we'll actually apply that very shortly, a little more later on. And then obviously the absolute velocity is the velocity of the body relative to some fixed datum, usually the Earth. Very important, I might throw one of those two mark definitions in your first test, just so this definitions, make sure you know what it is. It might be for 2 marks at the start of the question. What is the definition of the resultant velocity? And these are the kind of wording I'm looking for here, right? So yeah, so without further ado, let's start unpacking some resultant velocity problems. Yes, okay, so I'm just going to get your notebook out, and we're gonna start solving problems. It's time for tutorial time. So the concepts again, resultant and relative velocity and absolute velocity, and we'll be trying to basically unpack these. So start with nice elementary examples, and we start to kind of beef it up gradually. So I'm gonna share my whiteboard now. Yeah, so everyone, I'll give you 2 minutes just to get your notebooks out, and once you guys are done, just send me a thumbs up, and then we can actually proceed in solving the examples. Is there any questions with the lecture so far? Notsipo, are you there? Michaela, are you there?
Well, yes, just my network is very bad here.
Is it Mr. Shongwe? Yeah, okay. Hi, Miss Mbambisa. How are you? Is it Mr. Garcia? So I'm just
Yes,
waiting
sir.
on you guys to. Yes, great. Hi, Mr. Mbambisa. I don't know if you also have a question. Okay. Just let me know when you're ready. Then we can go. Just get your books out. It's time to get working. We're gonna be doing quite a few examples. I'm just having a look here. We'll be covering two different types of concepts. Yeah. And we all have a break. I think at around 10, obviously. I think our lectures ended basically at 12. So yeah, just before 12. So once you're good, just send a few thumbs up, then we can actually just proceed. Mr. Sozino, yes. See everyone is good. We'll begin now. Do you have a question? Or you raise your hand or you. Oh, nice. Okay. All right. So, first question, right? Let's just quickly, everyone can see. Nice. So, what we have here, always got these fun elementary examples. So, we've got a truck. I think this looks like a truck. And we've got Tashriq standing over here. And Tashriq, the truck is moving at a particular direction. And the truck is moving at 72 kilometers per hour. Right. And what happens here is Tashriq has a catapult. I don't know if you know what a catapult is, a slingshot. I don't know what's I forgot the normal word. Is it called a kitty or something? If I'm correct. That's over there. And what's happening is now he's going to be shooting a stone, and we're going to be looking relative to the road, right? So we are going to be standing here. This is all of us holding hands, and we are looking here. What is happening, right? I hope this illustration is making sense, right? Okay, so in the first scenario, shouldn't actually put the answers there, but anyway, Tashriq is shooting the stone this way. So I'll just make the arrow for that's for this way. So the first thing is first, we want to convert, and you're shooting a stone at 20 meters per second. So just, we have to first convert our figures over here. How do we convert this kilometers per hour? Who can tell me to meters per second?
Divided by 3.6.
100%. Thank you very much, Mr. Casimiro. Spanj, I don't know if you raised your hand there. So if you divide, yes.
So isn't the direction of the red arrow supposed to go the other side? Isn't it going away from the?
It's directly ahead. It's in front of him. Then directly backwards is the other way. Ahead of him. Yeah. So if you say 72 divided by 3.6, what do you get?
20.
20 meters per second. Nice. Okay. So we can erase the 72. So be aware of that conversions, guys. It's still there. It's still present. Right. So we know that it's going. So now, relative to the ground or relative to the road, right? What is the velocity? So can we say V, the vectorial sum here? So V, what's the stone relative to the road? We're gonna call the road O, or we can call it R, whatever. O just meaning, you know, the earth, whatever. That's gonna be, assuming this is positive. That's very important. Right is positive. That's gonna be 20 and what? Plus 20. You agree with me? Are we all happy with this? 40 meters per second. You guys agree with that? Simple now. It's gonna get fun now. It's gonna get fun. There we go. Thank you, Vian. So the next part at B, what are we doing now? Stone relative to the earth. That's directly backwards. So we close that up. And backwards meaning Tashrik is shooting his kitty that way. So relative to the ground, what's gonna happen now? What's the velocity? It's gonna be 20. Can someone tell me?
Minus
20 exactly. Simple. So relative to the ground doesn't look like at a particular instant that stone is standing still. Very interesting, right? Yep, nice. And now I see who's sharp here. So let me just erase this. Next scenario. So now we're getting to more vectors. So what they're saying now, he's shooting the stone 20 degrees. I think I have to remove that Tashrik now. Just removing. He's shooting the stone now 20 degrees in the direction the truck is moving. Right. And it is still 20. So now they're asking what is, and it's obviously still at 20 meters per second. That hasn't changed. That's where the stone is going. What they're asking now is what is obviously the initial velocity, obviously, right? The velocity of the stone relative to the road. How do you think we're going to solve this? Who has any idea? What do we normally use for forces and vectors? I'll give you guys a minute to process. How do you solve your vectors? Components, yes, he calls it components. So obviously what we can do is adopt all of this on a Cartesian plane. Right. Fantastic, Vian. We resolve the components. The way I understand the stone will be 20 meters per second. Now we need whatever velocity the truck will contribute the stone to that angle. I'm not sure Stone between it. Now I understand whatever velocity the truck will contribute. Yes. It's the resultant velocity essentially. I think that's what you're kind of saying. What the truck is contributing to the stone is. So what we have first of all is VRT, which is the VT. It's truck, which is 20 meters per second. And then we have our let's say our stone at 20 degrees. So now we need to find, and that's V stone, and this is going to be at 20 meters per second, so 20 meters per second, so almost 20 here. All right. So now I'm going to give you guys a chance to brush up on your components. So what I typically do, I have a table, right, just to make things a bit neat. So I'll give you guys time to draft this table. So like this. Oh, got body. We've got truck. We can call it VT. We've got VS. And we've got the X direction. We've got the Y direction, and then you can say maybe maybe over here we can actually just do the sum. I don't know how you guys typically used to do it. So if you're saying that correctly, what you're basically doing is, and we're adding as I said to the resultant velocity is the vectorial sum, right? The vectorial sum of the velocities. Okay. So I'll give you guys a minute to do the table, and then let's see if we can compute it. So this is a lot of the problems going to be, you're going to have two bodies moving, right? You're going to start seeing, it's going to all start, but the concept must obviously give birth to itself. So Ms. Pandje, what are the components for the truck? Can you please give it to me? Let's start with the truck and then the stone. Ms. Pandje, can you hear me? I'm still trying to do the tables. Okay, I'll give you guys till 5 to get the table. But obviously you get the idea of what's going to happen here. You know your components. Oh, great. Okay. Just give everyone some time to, obviously this is maybe some rust. It's still second week only. We still have a bit of some rust in. So, Nosipo, are you there? Are you following? So another student who's not here actually. Hi, Nosipo. Oh, you are there. Okay, nice. I'm glad you're here. PJ, have you solved? Have you got the answer ready? Yes, nice. So it's 20 cos 10 plus 20. So I typically work it like this. 20, right? That just stays 20 and 0. And for the stone, it's going to be 20 cos 20. And this is going to be 20 sine 20. Important to note, it is positive and positive, right? It's the positive the quadrant. Be aware. It's in the positive quadrant. Okay, I'm going to test you guys now on something else. Nice. Okay. Just get that sum. Let me just zoom it in a bit. I know it's a bit messy. Let's get the sum. Where's my calculator? All right, let's see. Rian, have you got the X components already, the sum of them? 38.794. That looks good. You guys got that? 20 sine 20, x 6,84. And of course, 38, nice. Of course, we just have to square all of these guys here, 794, if you remember, final resultant, 6,84 squared. So obviously there's a bit of a warm-up. So you get 39,392 meters per second. So that's actually how fast the stone is going relative to the ground. So as you're watching, the stone looks much more faster. In fact, it is much more faster. I like to know how to get the direction. I'll leave that up to you guys now. I'll give you guys fantastic response. 39,39. So remember, and I'll bring out some more questions. I'll try to expand this a bit. So I want some to just kind of figure out the angle in the meantime. Let's see, 10 degrees mentioned in the question. Yeah. And how do we get that? That's going to be our O's are y over our x. If you remember that, 6,84 divided by 38.794. And you should get an answer there. 6,84, 38.794. And you get 9,999. If you guys get that, which is essentially 10 degrees. How did you guys get 11.9? You guys are off somewhere. Check your stuff. And what they mean is that it's 10 degrees. Remember, we go anti-clockwise, so it's over there. And that makes sense, right? So you draw your typical parallelogram. That's what we're gonna see. So in this case, that stone velocity vector is going at 39,39 at 10 degrees. Are we all happy with that? Do we have this? Very important, guys. This is the core of what's going to be happening. You're going to be taking you're going to be doing this a lot. All right. That's the idea. So the stone relative to the the truck, obviously, it has two components over there, but I mean, we're going to call it 20 meters per second. Relative to the road, we're 20 meters per second. So it's very interesting, right? And obviously, for us looking at it, that's how the stone is going to actually project at that particular angle. We're just talking 2 dimensions. We did do the direction now. Did you not see it, Nosipo? 10 degrees. That is what we are titling direction. I think she just left now. Okay. Okay, is everyone happy with this? So we can go on to D. So I'll give you guys 5 minutes to do D. See if you guys can figure that out, and I will come in. So, and now they're saying we're shooting the stone at the right angles basically to the road, right? So maybe I should erase all of this. So let me just sketch my truck. Just maybe over here. Just basically just think that it's 90 degrees without making it too complicated. No, we don't want to stall. So over here, truck is still moving at 20, and let's say the stone is going that way, for instance. I think that's to the left of the truck, 20 meters per second. So they're basically they're 90 degrees apart from each other. Let's see what we get. Are you guys still following? Nosipo, you asked about the direction. Did you yes, Ms. Panje?
So I was gonna ask, because it says at right angles to the road, to the left it's the truck, which means it's at the back, obviously, but is it up or down? Because that's important when we're doing a component. Is it
exactly.
not?
Yeah, it is. But let's just call it down for now. You're definitely right here. But I'm just saying down for the sake of, yeah, it could have been up exactly. You're definitely correct. Let's just call it down. Yeah, that is definitely correct. Yeah. Because it could have been up, right up in the sky or downwards, definitely. Thank you. Nosipo, I hope you got the direction right for the previous question. And that's how you get that. So I'm waiting for everyone to kind of just do this. We can actually find this one quite simply. It's just 2 vectors like this. You can even do a table if you want. Nice. And obviously your resultant will be there. That's 20. And that's 20. You can actually just do, nope, looking last, your resultant is not like this. This is resultant like that. Yeah, you could have just done this. Let me just go on my table. It's going to be fairly straightforward, this one. Your x direction y, vt, vs, 20, 0, 0, 20. I'm going to call this negative. Obviously, your stone relative to the ground, or your resultant velocity of the 2 is going to be 20 squared plus 20 squared. And you should get 28,28. Did you guys get this? Then obviously your angle will be the same. You know, it's assuming one is negative. Most finally did raise a good question, and you would get negative 45 degrees. And what it means, it's basically it's 45 degrees over there. And I think they do state a relative bearing of 315, which makes sense. Yeah, because it goes that way, yeah. So let's say 45 degrees. And it's just important to note that negative 45, it's going clockwise and not anti-clockwise. So Shiri got it. Did everyone else get that part? Nice, Rian. So this is what it's about. It's essentially, yeah, we're getting there. By the end of the lecture, you'd have gotten the key components of what this chapter is about. Right. So relative to the ground, we see 28,28 meters per second at 45 degrees. That's how the stone will be traveling as we'll be looking. Any questions, students? There's still the basic stuff. So what we're gonna do one more big question, and then we'll move on to the next part of the work. Yeah. Very important to know how to do your components. It's gonna come up. Okay, so I think everyone's happy with that. And now I can actually, so we're still practicing. We're not actually gonna oh, actually there's like two. Well, we have to probably leave the one for but anyway, we'll see. I'll copy this one. My simple one as well. I'll give you guys now, let's say 5 minutes to do this one. Not 5, make it around 5 minutes. All right, hope you guys can all see that. See, this is a nice practice. So here we got a hot air balloon, and it's rising up at 2 meters per second. A vertical, it's obviously going straight up, and obviously you have some wind blowing from west, pushing it at a speed of 1.2 meters per second, and it's released at 8 o'clock. Nice. So what I want is the resultant velocity of the balloon. So obviously looking from the ground, how the balloon is being drifted. And then the second thing is how far from point P will the balloon be at 10 minutes past 8. All right, so this is an interesting one. So I want to see you guys give this one a go. I'm going to give you guys around 5 minutes, and then yeah, I will come in and do this one. Are we all clear, guys? So just attempt this one as an exercise. Has anyone got it yet? The resultant in velocity at least? Nice, Mr. Duplessis, nice. I wonder if we can find part B now. Nice, Mr. Mula. Let's see. And let's see if we can manage to do B. Nice. Have you guys solved part B? I'll give you guys a minute and I'll step in. Vian has got it. Okay. Who managed to solve part B? Quite interested to see. Hope you guys are enjoying this chapter so far. It's going to get fun. Tashrik. Okay. Right. So I'll come in fairly simple. Not going to still go hardcore in. We've got the win this way. We've got the so this is the A, the wind, sorry, the wind is going at 1.2, the balloon is going at 2 meters per second, and our resultant over here will be we can just use Pythagoras over here. So what can we call it? VBO, O being, relative to the ground, that's the resultant velocity. You could have called it VR, that's perfectly fine with me. Notations are not important yet, but that will just be 2 squared plus 1.2 squared. Let's see, 2 squared plus 1.2 squared, get an answer of 2,332 meters per second. And obviously, we would like to know the angle. Obviously, this is also 1.2 over here. And we can say tan tan 2 over 1.2, and we can find this angle over here, and that's going to be 59,036 degrees, right? 036 from the horizontal, right? 04, right? So basically what they're saying is that this balloon is going to be going something like that. All right. And now they're asking how far away from point P basically after 10 minutes, how far from point P will this be? So who has any idea of how to solve this? I'm quite curious. Tashrik, Vian, Mr. Garcia, the last hands I see there. Speed times time, beautiful. I want to say speed times time, but we're assuming, particularly in this example, we're assuming a constant velocity. Right. So if you assume a constant velocity, it's going to be S equals V times T. I'm sure you guys remember that from Mechanics 1. Yeah, speed times time. Yep, that's the distance. Obviously, we get units, meters per second squared, and second, we're left with meters. So velocity is 2,332 times 60 times, what's it now again? 10 minutes, right? So it's 10. 10 minutes, we get that into 60 seconds, and I think we get an answer of 1399. Beautiful. Yeah. Every second it covers. Yeah, there we go. Nice, Tashrik. You're getting it. So that's 1399. Oh, 1399.2. So this is also, I'm bringing out, as you can see, each example is bringing out new new flavors, so to say, of the you know. All right, nice and simple example. So this is a very important thing. You're typically going to be asked for time. How long will it take? How far will it move? You'll see. So any questions on this one, students, before we move on? So I'm going to do one more example. Then there's a lot of practice examples in the slides you can actually do. And obviously we can when I see you on campus, we can actually talk to one of them, talk to one or two of them, and then we can continue with obviously the lecture. So I'm obviously not doing everything for you, but the core concepts must be here. So is everyone on the same page? Bones, are you good? Johan, Mr. Asa, I hope you're following. So any questions on this example? Nice and easy. Nice, Ms. Pandey. Thank you. Nice. Okay. Mr. Silva, be quiet. Thank you, Ms. Mamisa. Yep. Okay. So you just do this one, and then we can go on a break. And then yeah, and then I'll introduce the next concept, which is relative velocity. It's also part of resultant velocity. So this is what we did. This is the second one, and this is now there's two practice examples which I'd like you to do. I'm curious to see. Obviously, we can discuss it as per what is this in the lecture. But here we got a boat type example, right? So I'm going to only copy the first part, and then I'll leave the second part to you. And the nice part about this is to basically see if you can understand the concept of in which direction they must particularly travel. And you should be able to get it. But obviously I'm leaving things for discussion. Just to make you aware, there's a mistake with the unit over here. There should have been 6 meters per second and 4 meters per second, not kilometers per hour, just to make that clear. So this is a similar type example. And now they're asking how far they land downstream and how long it takes to cross the river. So I'm going to give you the first part. You can take around 5 minutes, 10 minutes to do it. I'll step in, I'll do it, and then we can actually, I would actually like to do the second part, but I will do the second part when I see you. So that's fine. So even the next part of the slide, I'd like you guys to think that as well. And obviously I'll show you all the stuff I've posted. Then we can actually start on this part. And this is the crux of what we're actually going to be covering for this chapter, this particular part. So without further ado, let's quickly see. Let's just quickly do this one. All right. So again, I'm going to give you some time to do this one. Then you can, then I'll step in. So very key important. That is why I said with online lectures, you're practicing for the actual, you're practicing for your tests while you work. All the stuff is relevant. Nothing is irrelevant. Very important. Okay. So repeat the corrections. Oh, it's just meters per second. That's all. So that's just meters per second. That's all. Okay. So what we have over here is our boat example, which is the same as any type example, and it's going to get fun, and you're going to see why it's going to get fun. And got something like this, and that is what we're looking at here. Okay, so obviously we don't have that. In this case, we've got 6 meters per second, so that's 6, and our tide is at 4, right? So asking a few questions there. What is the resultant velocity? That should be easy. How far downstream should he land? That's going to be fun. I'd like to see you guys do that one. And how long will it take? So I can see this one they're asking how long in this case. Not the one is asking for the distance and the other one's asking how long. So I'll give you guys around 5 minutes to play around with this one, and then we can end this one, and then yeah. And then we can take a nice break, and then we can come back. Okay, guys. Giving you the 5 minutes now. Are you guys winning? Have you guys gotten who's gotten B and C? Yeah, Tashrik.
Now I'm just saying I got it, sir.
Oh, nice, well done. So you got both of them. Good, that's you're on the right track here.
Yeah, I got both.
Okay, cool. I'm happy. Mr. Shongwe. Plug and play, plug and play. Okay, guys, it's 5 past now. So let me quickly do this. The resultant is fairly easy. I don't have to be fancy about this. I can just obviously know that's the right angle, so we can just take the so we say the velocity of the boat relative to the ground. VBO will be 6 squared plus 4 squared. It's gonna get fun soon in the next part. 6 squared plus 4 squared.
Still working on it, sir.
Okay, noted. You should get your nice answer of 7,211 meters per second, and obviously your angle, you're going to take the tan of that, which is always your vertical divided by your horizontal. Let me see. It's 6. So it's, sorry, it's 6. Sorry, it's 6 before. It's 6/4. And you should get an answer of 53,31. So 309. 6/4. 53,3099, or just call it 53,31 degrees. What you're basically saying is that, looking at our diagram over here, should use another color. This guy over here is 53,31. Of course, the velocity vector is at 7,211. Right, that is simple.
It's 56.
Oh, 56. Thank you. 56. It's not 53, it's 56. Yep. Definitely. Right, 56, 56, 56. Okay. So the next part of the question, 56,31. They're asking, so obviously what you're expecting here, let's just copy this over here again. To copy all of that. What you're expecting is to move. So at B, you are initially expecting to move right across the river. Obviously, this is not the case, and you are obviously shifted from B to C. I'll say that again. So you're on the boat, you think you're going to go across, but obviously the tide is pushing you, and as it's pushing you, you're going to C, right? So they give you the width of the river, and the width of the river in this case is 660. So that is A to B. And they want to know basically the distance from here to here. So you know this angle over here. This angle is the same as this angle over here. This angle over here is basically 56,31. Then obviously that's a perfect 90-degree triangle. And this is going to be, what is this now? What's 90 minus that? That's going to be 33,69. So what we're looking at is this triangle over here. Nice. This triangle over here. And now you can use simple tricks to find BC. So if I look at my tricks, if I remember my tricks right, that should be 10, I think, opposite over adjacent. So 10, 33,69. Obviously, there's one way of finding it. It's going to be BC over AB. And of course, this is equal to BC over 660. I hope I'm correct. Does it make sense to everyone? First thing is first. You thought you never need tricks again. Welcome to S3. Have you guys agree with my analysis? So we're going to be moving a certain, I don't know how much. Does everyone agree with what I've done there? Nice, Tashirik agrees with me. Fantastic. So, okay, so you should get, obviously you can recap this on the recording, you should get 439,99. Okay, 439,99 millimeters, right? I shouldn't have said the whole thing is like that, but yeah, okay. So this angle is the same as that angle over there, actually, just put it like that rather. Okay, that's using your corresponding angles. Okay, approximately. So you land approximately 440 meters away, not millimeters, sorry. To use to millimeters. Now, the next part, they're asking you, how long will it take him to cross the river? So this brings out some new stuff, right? So obviously we know distance equals velocity times time. Okay. Now, before the ones you've solved this, you can keep it to yourself for now. But I like to ask you, which distance and velocity do we use? Which distance? I just want to open a discussion. The ones who know, just give it a few seconds or just a minute before answering. But which velocity do we use? Do we use 3, 5, 7.2, 11? What is our velocity and what is our distance used in order to find the time? I'll wait on your responses. Johan, Mr. Duplessis, Luando, Mr. Vieira, Mr. Melelo. Guys, have I lost you here? The distance that the boat travels and the speed it actually travels. Mr. Duplessis says 440. And that 440. I agree with his velocity. I don't agree with his distance, but I agree with Tashirik. The distance the boat actually travels and the speed it actually travels. That is spot on. And you guys would think so. Tashirik has dropped the hint there. I'd like to know what is the velocity the boat actually traveling at and what is the distance it's actually traveling at. B, with the Duplessis, that 4399 is not the distance. It's the resultant distance. There we go. That is what I'm looking for. It is the resultant distance. So back to this drawing over here. Remember we had a 660. We had a 33.69. Don't be shocked if you see a problem similar to this. It's definitely possible. It is a exam type, test type problem. This was for 40. And if you recall, this is the direction it's traveling. Just give me a moment. My pen was just this here, this line over here. Just give me here. Let's make it thicker. Remember this line? That's the way it's traveling, right? That is the way it's traveling. Okay. Nice. So we need to find, so we already have the velocity vector, which is 7.221, but now we need to find the distance here. And obviously this distance, Ms. Panji, I hope you're following. Are you still there? That's going to be 660 squared plus 440 squared. Right? You could have done it a different way, obviously, as well. So you should get 793.22 meters. And we know distance equals velocity times time. Therefore, time will be distance divided by velocity, and that'll be 793.22 divided by the velocity, and the velocity was 7,211. I think, but obviously this other meters per second, so we're fine. Yeah. So I get 110.0015 seconds. Are we all happy with us so far? Critical stuff. I'm so lost. Oh. What are you lost, Ms. Panjay? Can you please take us back? Can you please ask a question?
I think it's not necessarily the concept per se, but I think it just helps when you're solving the problem and then you can see the question, then I can just like refer to it every now and then. So now I'm just a little bit confused.
Okay, yeah, so all what's happening now, I'm with you, yeah. You put, yeah, I should actually post the slides before the lecture, maybe then. We're asking how far downstream does he land? I hope you got that part. So what I'm saying is from here, from B to C, that's the first part we did. So instead of you thinking you're going across from A to B, the tide will eventually push you to C, and we found out with that CERN that it was 440 meters away from B, right? Secondly, they're asking how long will it take for him to cross the river, and what I asked was which distance and velocity to use. So Tajirik mentioned we have to use the actual velocity and the actual distance traveled. And the actual velocity was obviously its resultant velocity. Obviously, that's with respect to the ground. It actually travels at the velocity. And to find the actual distance, it's going to be that 660 and that 440 over there. And we find the total, that distance basically, right? The actual distance to travel. Once we had that, we have constant velocity formula. When our body travels at a constant velocity, and we can just simply say that distance divided by that and get 110 seconds. That's where we are now. I hope everyone got that. I'm actually going to post the slides like in the break time. Is everyone clear with that? Miss Annelisiwe, you got it? Michaela? So the next step is obviously we want to convert this guy. Typically, we don't leave it in seconds. We want to convert this into minutes and seconds. So we say 110 divided by 60, you should get 1.83 that's second, 1.833 minutes, right? And how do we get it into seconds now? So we know it's 1.83 minutes. What I typically do is I say, for me to get it into seconds, I say -1. I get 0.833. And I times that guy by 60. If I do that, I should get my seconds now. And my seconds will be 50. So it'll be 1 minute and 50 seconds. So I hope you guys know how to do that, at least. Yeah. Spanish says thumbs up. Okay, great. So that's all. I mean, this is a quite decent question. It has a second part, which obviously you're going to play around with and see. But it'll take 1 minute and 50 seconds for it to cross the thing over there, right? So it probably would have been a bit faster, you know. Could have actually played around with this question, but yeah. Guys, are there any questions before we depart on our break? We can have a nice 20-minute break. Then we can proceed with the next. I'll talk to you in terms of the next part. You know, it's still early morning here. Some people are still rusty. Any questions, guys? Can just get a few thumbs up, and then we can depart on our. I'll stop the recording. I'll continue once we return. Very, very important stuff here. Yes.
So, could you please explain me about these angles, 33.69? I'm a bit
Yes.
confused.
Okay, so if you look over here, remember the angle we found here was 53.6. This angle here. So it's just the co-angle of that one. So this is 56.39. So we just say 90 minus 56.39. It's just so that we can find. So just that we can find this over here.
Oh, okay. I got it now.
Yeah.
Yeah, I got
Nice,
it now.
nice.
Yeah, thank you.
100%. Any other questions? Guys, you're here to ask questions. You know, that is why you pay your school fees. You're here to get some knowledge.
Sorry, sir.
Pass exams. Yes.
Yes, I wanted to know if we could as well calculate the results from the point CB. There on the point C,
CB.
the angle wouldn't be the same as on A.
Oh, do you mean like you could have the resultant of this over here? This.
Yes, if we
Yeah, you
could
could have
find from
done.
the point C.
If you put.
On point C.
Yes.
Yeah, the angle should be as well as I think 56, no?
Yes, correct. Yeah, 100%. Alternate
Okay,
angles.
okay. Yeah, just
Yeah, you could have done it many ways. Yeah.
Okay,
Different ways
okay,
to do it.
fine.
You could have done sine, cos, tan. I just did it a quick way. Yeah.
Okay, fine. Thank you.
Yeah. Okay. Any other question before we have a break? Okay, what time is it now? Let me see. Okay, 10. Okay, guys. So let's have a break. And then we can come back at 1:45. So that's around about 8 minutes. Yeah. Let's come back at let's have a tea break. Till 10:45. So maybe we can get a coffee in, get something to eat, and then we can introduce a new concept. Not a new concept, it's still the same, but it just kind of talks to this very important concept which you're going to be dealing with. Yeah. Okay. In the meanwhile, check your Blackboard. I've posted some stuff. It's a nice summary of what's going to be expected for the chapter. There's a tutorial, there's another tutorial, and yeah, you eventually see. Yeah. Okay. Anyway, have a nice break, and I'll see you at 10:45.